The beginning of the universe, Robert Altman. Robert?
So the picture you see behind me is one projector now? Okay. So the picture you see behind me is the Hubble Extreme Deep Field, which is a little bit more of if you're not familiar with the Hubble Deep Field, the Hubble telescope is focused on one patch of the sky, one blank, dark patch of the sky for a long period of time and developed this picture. And then the extreme deep field went a little bit further. But what do we see here? We see lights and things. Each one of these small specks is a galaxy. Each one of these tiny things is a huge array of stars of vast proportions. And what this showed us is the universe is a huge place, much bigger than we ever reached. Even though we understood what it was and how long it's been around, it showed us that it's even more immense than we ever really conceived. And I want to talk to you a little about what brought us here. So the universe is a fascinating place. It's been around 13.77 billion years. That's 13 with 9 zeros after it. Yeah. So that's a long time. But what got us there? Well, when the universe started, it was infinitely small. And it was infinitely hot. And there was infinitely little time. I mean, just nothing. And as time started to move forward, time started to expand. Time wasn't even time. As this whole ball of everything and anything started to unravel and started to come into existence, it was the seething mass of what we call quarks and gluons. So let me put a couple terms up here. Quark is essentially a fundamental particle. Smaller, the strong force also operates at a smaller scale. So quark, there are 6 types of quarks: up, down, charm, strange, top, and bottom. And then the other term I want to write down is gluon. Kind of like a messenger on a moped, taking letters from one law firm to another or to a client's. The gluon is a carrier particle. It actually does the work of the strong force. So these are 3 fundamental concepts at this point. And at the very instant the universe began, the universe was a seething mass of free-floating quarks and gluons. There was no strong force. It was too hot for these things to actually start doing their jobs. So at the time that this started to actually function, that the strong force started to come into existence, we're talking about Let me back up 1 second. We have the first thing called, that's referred to as the plant epoch, up to 10 to the negative 43rd of a second. That's a billion, 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 billionth of a second. The temperature is 10 to the 32nd Kelvin. These numbers don't even have any meaning except for how large they are. At 10 to the negative 36 seconds, the temperature is cool enough so the strong force actually starts to emerge. Quarks and gluons start to form. This is where the universe just began. I've got notes here, I could go up to 10 seconds just to give you a sense of how the universe started. And we're still talking about a billion, 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 billionth of a second. We start to see the emergence of the first fundamental force. And quarks and gluons start to be able to interact to create matter. Actually, I take that back. Quarks emerged at 10 to the negative 6 seconds, about a millionth of a second. Right now, everything is still just seething mass, and the forces are starting to emerge. So, with that, hopefully I've given you a sense of the immense proportions of minuscule time that the universe operated on in its very brief beginnings. And stay tuned. Next time, we'll look at what happens slightly after that.